Look out at the cosmos. Billions of galaxies. Trillions upon trillions of stars. And one profound question: is anyone else out there?
We want to find another Earth. Is there a pale blue dot orbiting some star out there in the galaxy?
The search is on for worlds that could harbor life.
We're searching for our own vision of ourselves out there in space. We're searching for our heaven.
We've already discovered more than 700 planets beyond our solar system. And yet these exoplanets look nothing like our own.
Boy, were we wrong. All these solar systems that we're seeing in outer space, we find that they don't look like our solar system at all. We are the oddball. We're the freaks.
These are nightmare worlds. And the cosmos is full of them.
We're finding all different flavors of hell, all these different ways that planets can go wrong. So that's where we are right now, searching for heaven, finding hell.
These are worlds where life couldn't possibly survive. Could we really be alone? A cosmic fluke in a universe hostile to life. We may soon have the answer.
Now we have discovered hundreds of exoplanets in outer space at the rate of over 1 exoplanet a week.
In a few years, that will probably be thousands. And in the end, there could be millions or even billions of these things waiting for us to discover them.
How could all of them be planets from hell? The quest for answers starts here, 63 light years from Earth. We've discovered a planet. It's even larger than Jupiter. And it has a serious problem. Its orbit is incredibly tight. It's closer to its star than Mercury is to our sun. And 30 times closer in than the Earth. The result is a superheated hell. But there's another reason why nothing could survive here. And that's the ferocious wind. The surface is battered by a never-ending storm. We can't see these winds with our telescopes. But we know the superstorm exists. Because of this. NASA's Spitzer Space Telescope. Spitzer can see things that we can't. It doesn't use visible light. Instead, it sees in infrared. It's a part of the light spectrum we don't see with our eyes. Infrared is heat.
One advantage of studying the universe in the infrared is it gives us this opportunity to see the light coming from planets around other stars. When you try to look at the light of a planet next to the light of a star, the star is hundreds of thousands of times brighter than that planet, which renders the planet very, very faint. But if we push into the infrared part of the spectrum, the internal heat of the planet, just as my internal heat, causes the planet to glow. Now it's observable and measurable.
Spitzer gives us something completely new. The very first weather map of a planet beyond our solar system. This simple image is a technological triumph. The colors represent temperature differences. But the map also proves the planet has hellish winds. That's because the hotspot isn't where it should be. One side of the planet permanently faces the star, so its center should be the hottest point on the planet. It isn't. Something pushes the planet's hotspot to the side, and that takes incredible force. Only a non-stop 6,000-mile-an-hour hurricane would be this powerful. Strongest winds on Earth. 8 times the speed of sound. A small shift on the weather map. Evidence of supersonic winds raging on an alien planet. Truly, a planet from hell. We're finding new planets at a staggering rate, an average of 1 a week. Each one could be an Earth-like heaven. But the more we explore them, the more hellish worlds we find. And some are so nightmarishly hot that they're more than uninhabitable. They shouldn't even exist. This Jupiter-sized gas planet is 256 light-years from Earth. In infrared, it shines like a star. Thousands of times brighter than Venus, the hottest planet in our solar system. It's a blistering 3,700 degrees. It's nearly impossible for a planet to get this hot. Its hellish temperature provides a clue to its appearance. Only an absolutely black object could absorb enough light from its star to reach such scorching temperatures.
If you were coming up on the night side away from the star, you would just see this blackness in front of you. Very little radiation, very little light. It would almost just look like the stars were avoiding a part of the sky.
Just as black pavement absorbs sunlight and heats up on a sunny day, the black planet roasts beside its star. We don't understand its atmospheric chemistry. There's nothing on Earth that can absorb so much light. The planet's only color comes from a scorching hotspot.
As you flew around to the day side, things would begin to glow red hot. There'd be a huge swirling storm, all red and glowing. What a hellish world.
Deep inside, clouds of titanium oxide swirl around a solid heart, 100 times heavier than Earth. Darkness visible, another world from hell. But some planets are even bigger, seemingly impossible puzzles.
Here's a mystery. Every astronomy textbook says that gigantic Jupiter-sized planets form way out in outer space where it's really cold. So why is a Jupiter-sized planet, what's it doing inside the orbit of Mercury?
Jupiter-type planets can only form far from their parent stars, out in the cold of space. A gas giant orbiting this close means these monsters can move. This is WASP 12b, a scorching vision of hell. It's so close to its star that its orbit lasts just 1 Earth day.
This world is so hot, it's over 4,000 degrees Fahrenheit. This is just crazy hot.
WASP 12b is one of the hottest planets in the galaxy.
We've never seen anything like this before. This certainly is one of the most violent environments in the universe.
WASP 12b is only 2 million miles from its star. Searing heat puffs up its atmosphere, giving it the density of styrofoam. In a big enough bathtub, it would float.
We actually think it's so close to its star that the gravity, the tidal effect of gravity, warps it into almost an egg shape. It's not even round, it's oblong.
Thousands of miles beneath the puffed-up atmosphere lies a solid core. It's rich in carbon, and the pressures are extreme. There could be mountains of diamond and graphite, and seas of liquid tar. But WASP 12b won't last long. It orbits so closely that its star is literally tearing it apart, ripping away nearly 190 quadrillion tons of gas a year. "10 million years from now, WASP 12b will vanish." The question is, how did it get so close in the first place? This is the birth of a solar system. In the center, a new star. Around it swirls a disk of microscopic dust grains. These are planets in the making.
The dust grains collide, and every time they collide, they merge, and so they get bigger and bigger, and so they sort of grow like the dust bunnies under your bed. And you have 100,000 years or 1 million years to make a very big dust bunny, and they get bigger and bigger and bigger.
Trillions of miles from the star, it's cold enough for ice to form. Ice picks up dust and gas, these gaseous clumps grow bigger and bigger over millions of years. Eventually, they become gas giants. In our solar system, the gas giants, Jupiter, Saturn, Neptune, and Uranus, all form this way. In the distant orbits we still see today. So how did WASP-12b end up so searingly close to its star? The answer? Gravity. This planet is huge, 40% more massive than Jupiter. Its immense gravity disturbs the dust disk it formed from, creating turbulence.
And so the planet creates waves in the disk, sort of density waves. And you can sort of think of them as like waves on an ocean.
The gas giant becomes a galactic surfer. Over hundreds of thousands of years, the planet rides the waves inward toward the star.
As the planet gets closer and closer to the star, it starts to feel the radiation from the star more and more, and so it heats up.
Surfing millions of miles from the cold outer reaches of the star system into the tight, scorching orbit we see today. An ice-cold world becomes a planet from hell.
Nobody had any real clue that you could form a planet 1 billion miles out from a star. It somehow moved in. That is incredible, but that's really the only explanation of how these planets got so close to their stars in the first place.
WASP-12b is bizarre, but it isn't alone. We've found many of these super hot, super close giants. We call them hot Jupiters. Battered by supersonic winds, blacker than night, hotter than hell. But these hot Jupiters all have one thing in common. There's no life here.
So these planets are just about as different from the Earth as you can possibly imagine.
In fact, we've now found over 100 of these things, rendering them so common that the question really emerges, which ones are the weirdos, them or us?
This planetary roller coaster has consequences. As they spiral inward, hot Jupiters cause chaos. They create a whole new class of planets from hell. Orphan worlds flung away from their star into the emptiness of interstellar space. Planets orbit stars. Between the stars is a vast sea of darkness.
We've always thought of space as being empty. That would be considered its defining characteristic. That's why we call it space.
But when planet hunters switched from gazing at stars to staring deep into space, they made an amazing discovery. Out of the darkness, between the stars, planets began to appear. First, one dark gas giant. Then several more. Eventually, 10 dark, starless planets emerged from the shadows of space.
I often wonder what it would be like to be on one of these rogue planets in between stars. The night sky would be perfectly black. It'd be festooned with stars. It'd be beautiful.
But if you were at one of these planets, you would be in a world of perpetual night. There would be no sunrise or sunset. There would be no warmth of the sun.
These planets formed around a star, but now they roam the darkness of interstellar space. Their journey here was violent, each one forced from its home orbit by the gravity of a hot Jupiter.
A Jupiter-sized planet is an 800-pound gorilla. Where does it sit? Anywhere it wants to.
Hot Jupiters are killers. As they surf in toward their star, their immense gravity disrupts the system. Hurling planets from their orbital paths.
It flings into outer space any small planet. So any planet unfortunate enough to be orbiting close to the mother star would be flung into outer space with a passing Jupiter.
These planets will never again feel the heat or see the light of a star. All the rogue planets we've found so far are gas giants, but perhaps there are smaller, rocky worlds too. Worlds that were once like Earth.
The large Jupiter-like planets are just easier to see, but there's no reason to assume there also aren't smaller orphan planets. Maybe as a Jupiter planet moves in toward the star and plays ping pong with the planets, even something like Earth could have gotten kicked out. Then you would have this cold, frozen little world, just streaking between the stars, dark and lonely.
These planets are victims of a violent gravitational battle. Frozen, orphaned Earth twins.
There may be hundreds of billions with a B of these planets roaming the galaxy. Now, there are only a couple of 100 billion stars in the galaxy, so that means these rogue planets may actually outnumber stars.
Right now, we find an average of at least one new exoplanet a week. As our technology improves, we'll see smaller and smaller planets orbiting stars, worlds with a solid surface like our own. But the first rocky planets we've found are nothing like Earth. These planets have been to hell and back. We have found hundreds of alien worlds. And now for the first time, we're finding small planets made of rock, just like Earth. Planets this size are potential homes for life. But instead we find more planets from hell. Weird, nightmarish, and uninhabitable. This is Coro 7b. A world of violent extremes. Two hells in one. It's so close in that its star looms 360 times larger in the sky than our sun. On Koro 7b, the first hell is unimaginably hot. The surface is a furnace, roasting at 4,700 degrees. Lava boils, turning the atmosphere into vaporized rock. When a cooler front moves in, small pebbles condense, and rocks rain from the sky.
If that's not a classic vision of hell, I don't know what is.
But that's only half the story. The hot side of the planet is locked, permanently facing the star. Beyond is the Twilight Zone. It's temperate here, cool enough to turn the lava oceans into solid rock. But this pleasant zone is narrow. Travel further, and you descend into a second hell. This is the dark side. The half of the planet that never sees the sun. Eternal darkness and savage cold. The temperature is hundreds of degrees below zero.
So one side is hot, another side is cold. You either have, fire or ice in the extreme, the coldest places in the universe and the hottest places in the universe. You couldn't think of a worse place to end up.
The planet was not always this way. Turn back the clock 1.5 billion years. Koro 7b is forming. But it isn't rocking. It's a gas giant. 100 times bigger than Earth. It migrates in toward its star. As it closes in, the star blowtorches gas from the planet. Its gaseous shell blasts off into space to reveal a rocky core. Koro 7b is the skeletal remains of a hot Jupiter. Its parent star has reduced this once massive gas giant to a rocky cinder. It's hard to imagine planets more extreme than Koro 7b. Yet they do exist. Rocky worlds, machine gunned by deadly cosmic rays. This is a pulsar, 7,000 trillion miles away from Earth. It's a kind of cosmic lighthouse. This unbelievably tiny world, just 10 miles across, fires an intense beam of radiation through space as regularly as an atomic clock.
A single cubic centimeter, the size of a keyboard key, actually has about as much mass as Mount Everest. Smash a Mount Everest into a cubic centimeter, the whole star, which is only about 10 miles across, is like that.
It's one of the most hostile environments in the universe. Anything nearby gets hammered by intense gravity and magnetism. No one expected to find a planet here. But this pulsar has 3. Small, rocky, near Earth-sized. They were the first exoplanets ever discovered, and the last place you would ever find life.
It's got a tremendous magnetic field. It's blasting out X-rays, so these poor planets are just getting cooked by radiation. The word Earth-like, I don't think could be applied to these guys at all.
The X-ray beam strafes the planets over and over, firing radiation 1,000,000 times more deadly than medical X-rays. Slowly stripping their surfaces away. These are sterile worlds.
Everybody admits there's no chance for life, at least as we know it, on the planets that orbit the pulsar.
Radiation cooks pulsar planets to death. The opposite hell is no better. Frozen worlds too cold for life. In the constellation Scorpius, 20,000 light years away, is a red dwarf star. Red dwarfs are tiny and relatively cool. And this planet is too far away to fill what little heat there is. It's so distant, its orbit lasts 10 Earth years. It's the coldest planet we have found in the universe. Its surface is a frigid 370 degrees below zero. This is a world made entirely of ice. Methane, ammonia, and nitrogen are gases on Earth. Here they form a frozen, toxic frost. Glaciers and canyons and cliffs of ice are the only terrain. Here, hell really has frozen over. Our search for Earth's elusive twin reaches another dead end. Perhaps we are truly alone. Or will our first tantalizing glimpses of an alien world, potentially perfect for life, change everything? Earth. The only habitable world in our solar system. But in a galaxy of hundreds of billions of stars, can we really be alone? It's a question that planet hunters are trying to answer.
The whole purpose, in my opinion, of the discovery of exoplanets is to establish our true place in the universe. Who are we? Where do we belong in the cosmic scheme of things? Are there other planets that can have life just like ours?
That's where NASA's Kepler Space Telescope comes in. Kepler lets us calculate how far a planet is from its star. That's critical in figuring out whether it could sustain life. Life on Earth is only possible because we're the perfect distance from the sun, not too hot and not too cold. Just right for liquid water, oceans, rivers, lakes, rain, and life.
You know, journalists say, follow the money. Astronomers say, follow the water, because water is the universal solvent that dissolves most chemicals, and that's where DNA got off the ground. And where there's liquid water, there could be life.
We're looking for planets that are not too close to their parent star, where all the water would boil away, and not too far away from their parent star, where all the water would be tied up in a frozen form. We're looking for that Goldilocks zone, where the temperatures are just right for liquid water to pool on the surface.
Once Kepler has identified a new planet, astronomers check whether it lies in the habitable zone of its parent star. So far, Kepler hasn't found a single confirmed Earth twin. But it has identified more than 2,000 planetary possibilities. And it's this sheer abundance of planets that gives scientists hope.
The important thing to remember is that even though we're finding all of these terrible planets that are just completely unlivable, is that we're finding lots of them. We're finding hundreds and thousands of these planets. And what that's telling us is that planets are easy to make. And that means that even rare things are probably out there in large numbers. Even if the Earth is a rare, precious jewel in our galaxy, there may be dozens or hundreds of them out there.
Kepler has opened our eyes to a universe full of planets. We can now guess at how many there might be in our own galaxy. 50 billion. 50 billion worlds just waiting to be discovered. And we think 1% could be in the Goldilocks zone of their star. That's 500 million planets, each with a chance of harboring life. Right here on our own doorstep. We haven't found one yet, but we're getting closer. This is Gliese 581. A red dwarf star 20 light years from Earth.
Gliese 581 is a tiny little star. If the sun were the brightness of about a 100-watt light bulb, then Gliese 581 would be like a little Christmas tree light, a tiny little fairy light, very, very small. This shifts the life zone in, because now if you want to be warm enough, you need to snuggle up right next to the star.
The star has 4 planets. 3 are too close and hot for liquid water. But the 4th is different. It's a rocky world twice the size of Earth. And it's right on the edge of the Goldilocks zone. In theory, if the planet has a thick carbon dioxide atmosphere, it could trap enough heat to have clouds, rain, and oceans. It would be a strange place to live, twice Earth's gravity, bathed in permanent red twilight. But right now, this weird world is the closest we have to a planet like ours. It's a promising start.
When we actually know for a fact that up there around that star is a planet like Earth, that's going to just fundamentally change how people look at the sky and how people perceive their place in the universe. So that's going to be a profound moment, not just for me, but I think for humanity in general.
Our goal is to find another Earth, but along that path, we are going to find more things than we could have ever possibly imagined. And that's the part I love about this the most. We don't know what craziness is going to be around the next corner when we're looking for more planets. I can't even imagine.
Two decades ago, the only planets we knew were right here in our solar system. Now, there are hundreds, all very different from our home. The universe is filled with hellish worlds. Super hot. Ultra cold. This is our solar system. 8 planets, more than 150 moons, billions of space rocks, dust and gas, all orbit a single star in a giant whirling disk 10 billion miles across. It's been this way for 4 billion years. Everything moves round in an orderly fashion, serene and stable. But our solar system is unusual. Elsewhere in our universe, orbits are nothing like this. They're unstable, chaotic, even destructive.
Even in the nearby universe, we see incredibly violent examples of orbits. Giant planets that hurtle in toward their stars. We see shock waves of thousands of degrees perpetuate through the atmosphere.
There are planets that dip right over the surfaces of other stars. Huge stars orbiting each other. Multiple orbital systems where there's just chaos and entire objects can be kicked out of the system.
Stars gobbling up other stars, black holes eating up entire star systems, galaxies colliding with other galaxies. That's the norm.
Earth is an oasis of water and warmth. Life flourishes because of how we orbit the sun. Earth's orbit is almost circular. We stay about the same distance from the sun all year round. The temperature here is relatively constant, and Earth's orbit has been stable for the past 4.5 billion years. Without this stability, we would not exist.
To create DNA out of the oceans takes hundreds of millions, perhaps even 1 billion years. And for that stability, you need circular orbits. And so without the stability of the solar system and the Earth's orbit, there's no life on Earth.
We owe everything to Earth's orbit. We get a gentle ride. In an otherwise violent universe, we've hit the orbital jackpot. Yet chaos is never far away. Even within our solar system, there are extreme and violent orbits where life could never survive. Mercury, the closest rock to the sun and the smallest planet in the solar system. Its orbit stretches into an oval shape. At its furthest point, Mercury is 43 million miles from the sun. But at its closest point, it's just 28 million. This close in, it's hot.
800 degrees Fahrenheit, hotter than a baker's oven. Also, because there's very little atmosphere on Mercury, you'd choke. And because there's no air to speak of, the blood in your body would boil and it would burst your skin. You would literally explode on the surface of Mercury.
But the temperature can also fall to 300 degrees below zero, 3 times colder than the coldest place on Earth. Mercury has the most extreme temperature variations of any planet in the solar system. But it's also proof that orbits don't just loop. With each revolution around the sun, Mercury's path shifts. Over thousands of years, the planet follows a daisy pattern. At the other end of the solar system, there's Pluto, 4 billion miles from the Sun. The further away an object is, the slower its orbit. Pluto takes 248 years to complete a single loop. And Pluto is an anomaly. Its stretched orbit is on a completely different plane from the major planets, and it creates an amazing spectacle. During most of its orbit, Pluto is a frozen block of ice and rock. But as it gets closer to the Sun, summer begins.
When Pluto warms up, the frozen ices on the surface of Pluto, these are water ices, carbon dioxide, even some carbon monoxide, maybe methane ices, they evaporate and you get a fog, and the fog gets thicker, and then you get thick clouds, and suddenly you have an actual atmosphere around Pluto that wasn't there before.
This atmosphere is thickest when Pluto is closest to the Sun. But as the planet heads back into deep space, the temperature plummets to 400 degrees below zero. It begins to snow, flakes of frozen nitrogen and methane.
As winter comes, these gases slowly begin to freeze out of the atmosphere. They may rain down in a snow-like way, but gradually they accumulate sort of a glassy, semi-transparent layer, a frozen atmosphere on the surface of Pluto.
After a bitter winter, Pluto drifts closer to the Sun, and the 248-year cycle begins again. Extreme changes like these remind us how lucky we are that Earth's orbit is stable and benign. But it's a delicate balance. The smallest change could kill us all. If Earth's orbit were closer to the Sun, we would be like our closest neighbor, Venus.
Venus is a pretty good example of what might happen to the Earth if our orbit shifted a little bit in from where we are now. Venus has this hugely thick atmosphere that traps all of the heat, and the surface is close to 900 degrees. If we moved even just a little bit closer to the Sun, we would become more like Venus.
Oceans would boil away. Our planet would become a desert. Life would be destroyed. A small shift in the opposite direction, and instead of boiling, we'd freeze.
You would have snowball Earth, the Earth completely encased in ice, and that's only by moving the Earth a fraction of its distance from the Sun.
The polar ice caps would expand. Oceans would freeze. A permanent ice age would begin. The smallest shift in Earth's orbit, and we die by fire or ice. Orbits allow life to flourish. But they can also cause chaos. Orbits are even capable of destroying entire stars. Our planet's orbit makes life possible. But most orbits are violent. Space is a cosmic freeway. Nothing stands still. Everything moves around everything else, thanks to a single force, gravity.
Gravity is the universal force of attraction that spreads throughout the universe itself. It's the force that holds stars together. It's the force that binds the solar system together.
All objects have gravity, so all objects attract each other. The more mass an object has, the stronger its attraction. That's why falling apples are pulled toward Earth. In our solar system, the biggest object is the Sun. It's 700 times more massive than all the planets put together. The titanic force of the sun's gravity pulls all the planets inward. But something stops them from falling in. The planets are in constant motion. They fly through space at incredible speed, not directly toward the sun, but sideways, creating a tug of war between the sun's gravity and the planet's speed. When the two balance out, the planet loops round the sun. We call this an orbit.
An orbit is simply the motion, the path of an object around another object due to gravity. So you can have circular orbits, you can have elliptical orbits. Even if I were to take a ball and throw it in the air and catch it, very briefly, that ball is in orbit around the center of the Earth. It's just motion affected by gravity.
Imagine what would happen if the sun had no gravity. The planet's speed would shoot them out into space. On the other hand, if the planets stopped moving, gravity would pull them into the sun. All orbits are a balance between gravity and motion. We like to think the universe runs like clockwork, everything neat and orderly. The planets moving in cosmic harmony. But that's wrong. Orbits can be wild and unpredictable. And the more objects there are, the more unpredictable their orbits become.
Things can get complicated when you have more than two objects all trying to orbit around each other. Then an orbit can actually loop between one object and another. Speeds can get faster and slower. An orbit doesn't have to be just one regular path.
The universe's creativity defies the imagination. Travel out beyond Pluto, halfway to the nearest star, and you find these. Comets, chunks of ice and rock. They float in vast clouds, frozen remnants from the dawn of our solar system. Every so often, one falls towards the sun.
They can start 1 trillion miles out and fall right above the surface of the sun. So when they're really far away, they're hardly moving at all. When they're whipping past the sun, they're moving really, really fast. And so these can be some of the most extreme orbits in the solar system. They can be so elongated, they're almost a straight line.
Comets travel at up to 1 million miles an hour. They're cosmic missiles, guided by gravity and speed. Comets show us how destructive orbits can be. Many plunge into the sun or crash into planets.
If a comet were to hit the Earth, perhaps 5-6 miles across, watch out. It would be a planet buster. It would be an object sufficient to wipe out all life as we know it on the planet.
But most comets miss. They fly in from deep space and out again on million-year orbits. But move beyond our solar system, and orbits become even more violent. Death spirals rip apart entire planets, shred stars, and even tear holes in space. The universe is unimaginably big. So there should be other Earth-like worlds out there. Scientists looking for habitable planets thought they would find orbits just like ours. They were wrong.
So now we're on HD 154088. And there it is. Looks good.
We have discovered hundreds of planets outside our solar system, but they're not like Earth at all. These are strange, alien worlds with unfamiliar orbits.
What we're finding among extrasolar planets is an incredible diversity of these orbital shapes and sizes. Some of the orbits are extremely tight around their host star, the planet going around in just hours or days. So we're seeing interactions and shapes and sizes of orbits that are like nothing we ever imagined.
Some worlds are so hostile, life as we know it would be impossible. This is WASP-18b. It's a hot Jupiter, a class of huge planets that closely orbit their stars. WASP-18b is 50 times closer to its star than we are to the Sun. It's so close, it orbits in less than 1 day.
If you had said, what's the weirdest, least likely orbit you could possibly imagine? I would have said, take something like Jupiter and plop it down right next to a star, 5 million miles away. And it turns out I would be totally wrong. That is an extremely common thing that we see in the universe. In fact, most of the planets that we're discovering around other stars appear to be in orbits like that.
This cosmic duel produces incredibly powerful physical effects. WASP-18b burns at 4,000 degrees. Thermal hurricanes blast across its surface, and both star and planet are distorted by vast gravitational forces, the same forces that cause the tides on Earth.
Everybody is familiar with the idea of tides. In the course of a day, the level of the oceans get higher and then lower. Well, that's from the influence of the sun and the moon, from the influence of orbits, things that are going around us or that we're going around. If you bring things closer together, tides become more extreme. Planets can actually get pulled into different shapes.
WASP-18b was formed in a cold region of space, far away from its star. Over millions of years, it spiraled into its present position. It's locked in a gravitational battle that can only end one way. Less than 1 million years from now, it will be consumed by fire.
The key conclusion you have to draw is when you see the universe today, it won't be that way tomorrow, and it won't be that way the week or the millennium or 1 billion years later because of gravity.
Our search for Earth-like planets reveals a destructive universe, from the deadly, missile-like orbits of comets to the searing paths of hot Jupiters. There are even planets that don't seem to orbit anything at all. Scientists have recently detected tiny fluctuations in the light from distant stars. The only explanation? A massive object between us and them. These rogue planets don't orbit a parent star. They are planetary orphans, all alone in space.
Planets, by definition, go around stars. So, boy, were we shocked to find rogue planets. Rogue planets are a contradiction in terms. Planets without a mother star.
Scientists think every rogue planet did once orbit a star, until gravity hurled them away. New solar systems are chaotic places. Planets tug on each other and dramatically change course. Some planets even spiral out to wander the galaxy alone.
The presence of rogue planets shows us that gravity is not just this attractive force which binds the solar system together, it can also fling entire planets into outer space.
A recent Sky survey suggests our galaxy contains more rogue planets than stars. We've discovered orbits we didn't even know were possible. Gravity and motion keep our universe in constant turmoil. Vast orbiting suns cannibalize each other. Violent vortexes distort space itself. And powerful forces flick a star like a spinning top. Gravity causes chaos on an epic scale, hurling planets to their destruction or firing them off into space. But the cosmic roller coaster gets even more extreme. Orbits become so violent, they rip chunks out of stars. This is HM Cancri, a binary star system 16,000 light-years from Earth. They're white dwarfs, small but incredibly dense. 1 teaspoon of white dwarf matter can weigh 5 tons. The stars are just 50,000 miles apart, 5 times closer than we are to the Moon. They orbit at more than 1,000,000 miles an hour.
We have 2 white dwarfs an infinitesimal distance apart, rotating around each other in 5.5 minutes. This is a world's record for an astronomical body in space.
The forces are immense. Gravity rips superheated gas out of one star and slams it into the other. Scientists believe this orbit is so violent, it warps the fabric of space itself. In the process, the stars lose energy, falling even closer. Eventually, they'll collide, creating a supernova.
A supernova is one of the most violent, energetic events in the universe today. You are blowing up a star. There's no way to describe that kind of energy.
Some supernovae are so powerful, they are second only to the Big Bang itself for energy and sheer power. They are so magnificent, they can outshine an entire galaxy of 200 billion stars.
Supernovas can create one of the weirdest objects in the universe. A pulsar. Pulsars are intensely magnetic stars. They fire out beams of electromagnetic radiation that sweep across space.
There are few things in the universe more dramatic than a pulsar. Imagine a ball about 10 miles across, rotating hundreds of times a second. With a density that's almost unimaginable, 1 cubic centimeter of this material would have as much mass as Mount Everest.
You would feel a gravity that is millions of times what you're feeling sitting on the surface of the Earth. You wouldn't just be crushed flat by this. You would be crushed into a paste that is only a few atoms thick.
Anything that orbits a pulsar too closely risks being torn to shreds. This is the Black Widow pulsar. It rips through our galaxy at 600,000 miles an hour. The shock wave is so vast, our telescopes can't detect it 5,000 light years away. Traveling alongside it, a brown dwarf, bigger than a planet, smaller than a star. The pair are locked in an orbital dance of death.
The Black Widow in some sense is like a vampire, sucking the lifeblood from this brown dwarf star, eating away at its hydrogen and helium fuel.
Radiation blasts the brown dwarf's gases into space. A pulsar just 10 miles wide is destroying an object bigger than Jupiter. Eventually, the brown dwarf will evaporate. A single pulsar has immense destructive power. But 2 pulsars together can change the shape of the universe. This is the only known double pulsar system in our galaxy. Orbiting at 700,000 miles an hour, their speed and mass make them spin chaotically.
It's incredible to think of the enormous forces gravitationally that these two stars exert on each other, causing the whole geometry, the architecture of the system to change and spin around like a top on the table.
The gravity of the heavier pulsar makes the smaller one wobble erratically. It whips around so violently that the whole star almost tips over, just like a spinning top. It can't last forever. 85 million years from now, the two pulsars will merge to form a vast gravitational abyss. The universe's ultimate monster, a black hole. A black hole, the most extreme object in the universe. At its center, the laws of physics break down. Time comes to an end. Gravity is infinite.
A black hole is a bottomless pit of gravity caused by the death of a star. There is nothing in the universe more mysterious than how black holes work.
If you want to talk about extreme orbits and extreme gravity, you're talking black holes. That is at the top of the list. Nothing has stronger gravity than a black hole. It is the mass of something like the sun or more, compressed down into a ball that's only a couple of miles across.
50 years ago, black holes were dismissed as science fiction, but not anymore.
Now we see them at the center of galaxies, wandering through outer space. Black holes, we now know, are central to the evolution of the universe.
We now think there may be 100 million black holes in our galaxy alone. An encounter with any of them leads to oblivion. This is one of the largest and hottest stars in the universe. It's 20 times more massive than our sun and 10 times hotter. Stars like this never live long, but this one is locked in a diabolic waltz, trapped in the grip of a black hole. The gravity here is so powerful, the star orbits at 500,000 miles an hour. The black hole sucks the star's outer layers into a vast, swirling disk. A disk so hot, it blasts out X-rays 1,000,000 times more powerful than our sun.
This configuration, a star orbiting around a black hole, is extreme and it's unstable. First of all, the black hole is eating away at the atmosphere of its companion star, but the star itself is unstable. It will one day undergo a supernova and perhaps leave a black hole in its wake. And then we'll have two black holes rotating around each other, one of the rarest sights in the universe.
Eventually, these black holes will merge to create a new, larger monster, and the cycle of destruction will continue. But this black hole is small. Other black holes take violence to a whole new level. In 2011, astronomers witnessed one of the biggest explosions ever recorded. A flash of radiation brighter than 100 billion suns. A gamma ray burst. It was a spectacular event. The burst came from a supermassive black hole at the center of a distant galaxy. It had been dormant, but something had shocked it back to life.
If you pass by the event horizon, an imaginary sphere surrounding the black hole, that's the point of no return. It's like the ultimate Roche Motel. Everything checks in, nothing checks out.
Several stars were orbiting the black hole at a safe distance. Then one of them got too close. The sleeping giant suddenly awoke. Immense gravitational forces stretched the star to its breaking point until finally it was torn apart. Debris swirled round the black hole, heated to millions of degrees. Two giant jets of gamma rays blasted into space at the speed of light.
A black hole has torn a star apart, swallowed up half of the material of the star, and ejected the other half in an event that is among the most violent things we have ever seen in the history of astronomy.
The event was so violent, we saw it from Earth 3 billion light years away. Black holes can suck in planets and rip apart stars. But gravity doesn't always pull things in.
Any high school student knows that gravity sucks. It pulls, it never pushes. But it's actually more complicated. That's true when you just have two objects. But the minute you have more than two objects, strange things can happen, and gravity can actually push you away.
You can get very close to a body, but if you come in at just the right angle and just the right speed, instead of colliding together, one object can slingshot the other one away.
Recently, scientists discovered stars hurtling away from our galaxy at incredible speed. Normal stars don't do this. So what could accelerate a star to hypervelocity? The answer was a surprise.
You can only eject stars at these very, very high velocities, so close to 700, 800, 1,000 kilometers a second. You could only eject these with interactions with the supermassive black hole.
Each hypervelocity star was originally one of a pair of stars orbiting a supermassive black hole. When they got too close, gravity pulled them apart. The black hole catapulted one star out of the galaxy at 2 million miles an hour. Eventually, the other was sucked in and destroyed.
The interesting thing here is that you can get a complete redistribution of stars. So you have stars that are in the center of the galaxy and suddenly they're ejected out into intergalactic space.
And it's out here in deep space that orbits are at their most powerful, smashing entire galaxies together to create the structure of the universe itself. Across the universe, extreme gravity is a force of destruction. The orbits of planets and stars can be chaotic, unpredictable, and violent. But on a truly cosmic scale, gravity is no longer just a destroyer. It also creates new worlds. These are galaxies, giant spinning clusters of stars, gas, and dust, 100,000 light years across. Galaxies orbit each other in the same way planets orbit stars. Gravity pulls them together. Their speed keeps them apart. But ultimately, gravity always wins. Entire galaxies smash together.
One of the most spectacular events in the universe is when galaxies collide. You're talking about hundreds of billions of stars, 100,000 light years across. Two of these things slamming into each other.
Collisions between orbiting galaxies take place over millions of years. Gravity slowly pulls them together.
And you get these two galaxies that merge like two fluids mixing together, and you get long tidal tails as they pass through each other, but then gravity brings them back together again, and in the end, you get a full-fledged, more mature, larger galaxy than you had originally.
On this intergalactic scale, gravity and motion are no longer destructive forces. Now, they trigger the creation of life itself.
You would think a galactic collision would be incredibly destructive, and in one sense it is, but in another sense it's a very creative force.
Colliding galaxies smash vast gas clouds together. Huge shock waves rip through them, squeezing the gas. Then something amazing happens, the birth of countless stars.
It's incredible to think about two galaxies that gravitationally attract each other and collide. What could be more destructive? But in fact, there's a power of construction in such mergers, because as two galaxies come together, the gases are compressed, and sometimes the gases are compressed so much that you get the birth of stars and the associated planets around those stars. And so in the titanic collision between two galaxies, you can get the birth of stars and planets and perhaps eventually life on those planets.
Sometimes these collisions trigger a chain reaction. Two spiral galaxies in mid-collision, creating stars and planets. But this time, there's a difference. Some of these new stars are massive, unstable, and short-lived. They explode. Each explosion blasts out new shock waves and triggers the birth of even more stars. Astronomers call this a starburst. It's the ultimate example of gravity's creative power.
A starburst galaxy is one that is creating stars at a much higher rate than we usually see in normal galaxies. And so it's amazing that you can have such a beautiful creative process coming out of something so violent and destructive.
Gravity and motion, the two forces that give birth to every new star, also weave together the fabric of the universe itself. Our cosmos is not random. It has structure. The universe is a vast, three-dimensional tapestry. Each of these threads and filaments contains billions of galaxies. It's the scaffolding that holds everything together, the cosmic web.
And we think about scaffolding of a building, it's just sitting there static. But in fact, this scaffolding is quite dynamic and quite amazing because all of the constituents are moving around at very high speeds, crashing into one another. Galaxies, stars, black holes, supernovae, all in this tremendous cosmic dance.
The cosmic web is incomprehensibly vast. Each thread is full of motion. Galaxies form, orbit, and collide, countless billions in a constant stream. Every filament is a galactic freeway with an endless flow of traffic. Each point of light a galaxy. It's rush hour 24/7, and sometimes there's gridlock. Every billion light years, several filaments join to form a knot. Whole clusters collide to form some of the largest structures we know of. superclusters. This is one of them, Able 2744. 5 orbiting galaxy clusters crashed together in the single biggest cosmic pileup ever discovered. Gradually, the 5 clusters merged and fused to form a single giant supercluster 6 million light years across. The incredible power of orbits can literally tie the universe in knots.
Structures in the universe have evolved over billions of years through their orbits and their mutual gravitational attraction, and they've built up into larger and larger structures. And it's all thanks to these same attractive forces that bring them together, but can also tear them apart.
Again and again, we discover orbits dominating the cosmos.
The atom is the basic unit of chemistry. In the same way, the orbit is the basic unit of the universe itself. If you understand all possible orbits, you understand the dynamics driving the universe.
Orbits have created a cosmos full of richness and complexity.
Orbits are changeable, they're chaotic. Things that we never thought were possible are in fact possible.
From the smallest scale to the largest scale, it's the gravitational interactions and collisions that actually make our universe the beautiful place that it is.
And behind it all is a curious paradox.
When we think about how we evolved from being single cells to what we are today, we tend to see it as a pretty calm process, don't we? With animals slowly transforming into other animals. But that's only part of the story. The reality is much more brutal and violent, with creatures hanging on for dear life while disaster after disaster threatens them with extinction. It's almost impossible to comprehend the immense time scale of our planet's lifetime. So imagine the whole of Earth's history compressed into a single day. Each minute represents around 3 million years. At midnight on our clock, 4.5 billion years ago, the planet was born. 2 minutes later, the first catastrophe struck. A protoplanet, Theia, smashed into the infant Earth. And in its wake, the first life appeared. By 8 a.m., there were shallow seas full of simple bacteria. Gradually, over the next 2 billion years, the planet stabilized, though life remained as single-celled organisms. Until 12.5 hours later, at 8:27 p.m., 650 million years ago, disaster struck again. The planet froze. Temperatures plummeted. Ice spread down from the poles. It encased the planet in a layer thousands of meters thick. A snowball Earth. Life had only just got started. Now, it seemed doomed. There are no traces of these ancient ice sheets left. They're long gone. But there are still clues that can tell us about this dramatic ancient ice age. The evidence is hidden away in some of the world's most remote places. These are the Flinders Ranges in the Australian outback. Today, it's one of the hottest and driest places on Earth. But geologist Jim Gehling knows that the rocks here provide direct evidence of our planet's frozen past. The area is so vast, the best way to investigate is from the air. There's a disaster story written in these layers of rock. You just have to know how to read it.
It's really like looking at a book made of rock. Every single layer has a secret on it. We look at these rocks as though they're a history book.
With the help of aerial photographer Tim Beyer, they spot an unusual rock formation in a dried-up creek. It's the evidence Gayling's been looking for. A 650 million year old rock called a dropstone.
A dropstone is an exotic piece of rock. They shouldn't be mixed in with mud and sand. They should be together in boulder beds or gravel beds. But there they sit.
The rock may look insignificant, but it's a major clue to the powerful forces that created the frozen world of Snowball Earth.
This rock shouldn't be here. It's sitting in a rock composed of mud, silt, sand, and gravel. And normally that's impossible. The whole lot now is one big rock.
There's only one force that can carry rocks like this around the globe, and that is ice. There's not a lot of ice in Australia today. So, to investigate how ice could have moved rocks around the world in the ancient past, glaciologist Shad O'Neill scales the sheer walls of the Matanuska Glacier in Alaska. It's the closest we can get to our distant icy past.
We're taking a look at the rocks that are being transported down the valley by the glacier. And to do that, we need to go down there.
Glaciers are nature's bulldozers. They smash everything in their path. They gouge stones and rocks from high up in the mountains and carry them down the valley.
Rocks as big as buses can be transported for miles across the landscape by a glacier. I mean, the longest glaciers are hundreds, if not thousands of kilometers long, so you can move rocks over long distances.
When the ice melts, it deposits debris at the base of the glacier. This glacier is only a few hundred meters thick, but it can still carry thousands of tons of rock.
The glacier brought all this stuff down from the mountains, and when the glacier melts away, it ends up looking like a building site that's been bulldozed.
The Matanuska Glacier transports rocks for over 24 miles. It's the same process that carried the ancient dropstones in the Flinders Ranges. But the glaciers of 650 million years ago carried them for thousands of miles.
Here's a great example of a rock that was picked up by the glacier, carried down valley, and then deposited. Very similar to what you'd find in Australia, where glaciers used to be in the past.
So the Australian outback was once covered in ice. But that doesn't prove the whole world was frozen over. The problem is that the Earth's surface is in constant, very slow motion, pushing the continents to different places. So it's possible that 650 million years ago, when the dropstones were deposited, Australia could have been much closer to the cold South Pole. Meaning the dropstones were carried by normal polar glaciers. The solution to this conundrum can be found in another desert. Death Valley in the American Southwest. The term Snowball Earth was coined by geologist Joe Kirschvink, who's been gathering evidence on the theory for the past 2 decades.
Death Valley has a series of rocks that are extremely important for understanding Earth history. It's a treasure chest.
Like the Flinders Ranges, it's not the kind of place you'd expect to find evidence of ice. But geologists have found dozens of glacial dropstones here.
Every time I come here, I see new things. There are those big boulders, and I see one at the bottom, and they're all dropstones. You can see that they're coming in from the top. This is one of the best places in the world to see this type of geology.
The dropstones Kirschvink has discovered here date back to the same period as those found in the outback. So this desert too was covered in ice. But the big advantage is that we know where Death Valley was 650 million years ago. Every rock has a unique magnetic signature. This allows scientists to determine the point on the globe where the rock was formed. To study this signal, Kirschvink drills cores from the rocks containing the dropstones and measures their magnetic field.
The Earth's magnetic field is formed by electric currents flowing in the middle of the planet. The pattern of that field allows us to measure the latitude that a rock forms at.
When a glacier dumped these dropstones here, Death Valley was inside the tropics. The results at the Flinders Ranges were even more dramatic.
A group started studying the magnetism in the Flinders Ranges, and they thought they had a very stable magnetization. That they said, well, wait a minute, something might be relevant there.
The rock's magnetic signal revealed that 650 million years ago, Australia was in a completely different place than today. When the whole continent was in the grip of a big freeze, Australia was near the equator. Here was proof the scientists were looking for.
It was wonderful. It was the first time anywhere that we had proven that the glaciers were on the equator.
Ice sheets along the equator, the world's warmest climate zone, meant only one thing.
If you have ice at the equator, then the whole of the globe must have been covered by ice. And so you have to envisage a completely white planet.
Scientists believe it was the greatest ice age in the history of the Earth.
The entire Earth would have looked like Antarctica looks today. Even areas as desolate like this in Death Valley with nothing on it would be under several hundred meters of ice. The whole planet indeed would be a snowball.
Under a thick crust of snow and ice, the simple microbial life developing in the oceans faced an uncertain future.
This was the greatest ice age that this planet has ever known. You have to imagine a planet whose oceans were not only capped by ice near the poles, but that ice had grown across the entire planet and all but shut down its living systems.
650 million years ago, life on Earth seemed destined for total extinction. Somehow, something had plunged the whole planet into a catastrophic deep freeze. The question was, what? "8:27 p.m. on our clock of the Earth's history, 650 million years ago. The planet faced climate disaster. A global deep freeze. But what made it happen? Snowball Earth wasn't the first time the Earth had frozen, and it wouldn't be the last. Our planet goes through an ice age about once every 100,000 years. Most of them are caused by changes in our orbit. The further away from the sun we go, the colder it gets. At the height of the last ice age, ice sheets covered around a third of the planet, and all of this would have been buried under hundreds of feet of ice. But factors like orbit and rotation aren't enough to explain ice stretching right down to the equator. That must have taken something far more dramatic. The smoking gun turned out to be our atmosphere. Specifically, greenhouse gases like carbon dioxide.
A greenhouse gas is any kind of gas which has the capacity to convert the sun's rays into heat, making this planet the warm planet that it is today.
But it's a delicate balancing act. If CO2 levels grow too high or too low, the climate spirals into chaos. Too much carbon dioxide and the planet warms, too little and it cools.
Carbon dioxide is a very important gas. It's both our dilemma and our solution when it's there in too great a proportion that overheats the Earth, which of course we're worried about today. However, in the time leading up to Snowball Earth, we had the opposite problem. There wasn't enough carbon dioxide, and the Earth began to cool to a point where there was a runaway refrigeration that locked this Earth up in an icy crust.
Gehling believes that a drop in carbon dioxide levels caused the Snowball Earth disaster. Something was removing the CO2 from the atmosphere on a huge scale. And there's only one process capable of doing that: weathering. Carbon dioxide mixes with water vapor to form acid rain. The acid reacts with the rocks it falls on to form new carbon chemicals in the water. It then washes down to the sea, where it helps form solid limestone. Carbon dioxide that was once in the atmosphere is locked away on the ocean floor.
When weathering occurs at a great rate, you strip away rocks with acid rain, and that takes carbon dioxide out of the atmosphere and makes sure that it's locked away in the ocean.
Weathering happens more quickly when it's hot and humid. Normally, at least some of the Earth's land masses are too far north or south for weathering to be a major factor. But 650 million years ago, all the Earth's land masses, from Death Valley to Australia, were clumped together into one big supercontinent at the equator. The weathering process went into overdrive. CO2 levels crashed, and so did the Earth's temperature.
You have carbon dioxide being taken out and not replaced, and as a result, the Earth inevitably has to cool until you have a snowball.
Today, plants and animals help balance the levels of carbon dioxide in the atmosphere. Plants absorb it, animals breathe it out. But 650 million years ago, the only life forms on Earth were single-celled bacteria in the oceans. And they were actually making the situation worse.
650 million years ago, this is a world of cyanobacteria. Bacteria that formed a slime layer on the seafloor. Cyanobacteria are tiny organisms that have been around on this planet for 3 billion years before Snowball Earth. But at this time, they were particularly important.
These cyanobacteria sucked even more carbon dioxide from the oceans and locked it into limestone reefs called stromatolites. Some of this ancient carbon dioxide is still trapped in fossilised reefs, like these in Flinders Ranges in southern Australia. When Jim Gehling pours a weak acid onto them, the carbon dioxide they locked away hundreds of millions of years ago fizzes out.
What you'll see is an effervescence. Those white bubbles are carbon dioxide that had been locked up in these stromatolites, being released back into the atmosphere.
Rather than stabilizing the carbon dioxide levels, the cyanobacteria were depleting them further. In combination with weathering, they sucked the carbon dioxide out of the atmosphere and temperatures plummeted. Even then, the planet might have avoided a total freeze until a catastrophic chain reaction pushed it to the point of no return. "30 seconds past 8:27 p.m. on our clock of Earth's history. Snowball Earth, 650 million years ago, and counting. Ice was creeping down from the poles. In a normal ice age, at some point it would have stopped, but this wasn't normal. The ice just kept on coming until eventually it reached a point of no return. As it did, it triggered a phenomenon that would push life to the limit. The Earth's surface is made up of land, open ocean, and ice. These surfaces all reflect sunlight differently, and that's the key to what happened next. This is the Arctic Ocean, at the point where the ice meets open water. Scientists call it the lead edge. And geophysicist Don Perovich is here to study how the ancient Earth tipped over into a catastrophic deep freeze.
This is the place where the ice that's frozen to the shore meets the open Arctic Ocean. But it's more than that. The lead is where there's water, the lead's where there's light, and so the lead's where there's life. We see whales going by and seals, and birds flying above. It's an incredibly productive area.
Here, Perovich can compare the reflectivity, or albedo, of two very different surfaces, the sea ice and open ocean. His sensor measures the amount of sunlight hitting the ice and the amount it reflects back. Sea ice is the most reflective surface on the planet. It reflects 85% of the sunlight that hits it.
If we were to just go out there, just 100 yards away to the lead, the albedo would be less than 10%. And what's interesting about this is this snow-covered ice has the largest albedo of any naturally occurring surface on Earth, and the open ocean has the smallest. So right here, we have a contrast between the best natural reflector and the worst natural reflector.
Open sea reflects very little light back into space. It absorbs the energy in the sunlight, keeping the planet warm. 650 million years ago, the opposite happened. Earth's best reflector, sea ice, was replacing its worst reflector, sea water. When enough ice had formed, the remaining ocean couldn't absorb enough heat. So more sea ice built up. That reflected more sunlight, the Earth got colder, and that made still more ice. It was the point of no return.
Let's say we grow a little bit more ice. So we're replacing the worst reflector with the best reflector. We'll cool things off, we'll get more ice, and we'll cool it off more, and it builds upon itself.
A runaway freezing effect capable of turning the whole planet into an ice ball. It's an idea no one even considered until a few decades ago. Scientists only discovered it was possible when they were studying another kind of disaster altogether. A nuclear war. During the Cold War, researchers predicted that a nuclear holocaust could push enough smoke and dust into the atmosphere to block out the sun and initiate a global freeze. Russian climate modeler Mikhail Budiko was investigating this scenario when he made a chilling discovery. He calculated that if the ice sheets spread beyond 30 degrees latitude, that's as far south as North Africa, they'd reflect so much of the sun's energy that the Earth would reach an irreversible tipping point.
So when we have a system like the Earth with these feedbacks, one of the things that's talked about a lot is tipping points. You can think of it as you're in a boat rocking back and forth, not much changes until you go too far, and then you're in a new state. And Budiko's work said that if we moved the ice down far enough, we'd reach a tipping point and cover the whole Earth with it.
Budiko calculated that if the ice ever reached this tipping point, the planet would no longer absorb enough heat to keep the ice in check. The planet would be entombed in ice from pole to pole. The theory is that 650 million years ago, this was exactly what happened.
Instead of the world we have today, we'd have something that looked like this. A vast expanse of white, of blocks of ice tilted every which way, covered by snow.
The planet descended into the most extreme and least hospitable climate it had ever experienced. Eventually, the ice sheets collided, clamping their icy jaws shut at the equator. It seemed that nothing could survive in this frozen wasteland. And yet, incredibly, it was this catastrophe that brought about life as we know it, and without it, none of this and none of the people around us would be here today. 647 million years ago, 8:28 p.m. on our clock representing the Earth's history. The planet was buried under ice thousands of meters thick. Deep beneath the ice sheets, single-celled organisms, the only life on the planet, faced a stark choice: adapt or die. Bacteria that had evolved over 2 billion years seemed destined for extinction. Imagine if Snowball Earth happened today. Could we survive? Temperatures would plummet way below zero, ice caps would spread out from the poles and engulf whole continents, violent snowstorms would paralyze entire populations.
You could not run a nuclear power plant long enough to get through the snowball.
Many experts believe we could find ways to live through a short-term ice age, but the odds of surviving a snowball Earth are next to nothing.
If humans ever experience a snowball Earth, we will quite bluntly be out of control. There is no way we could stop it. It would be easier to live on the surface of Mars, probably, than on the surface of Earth during a snowball.
Without food to eat or fuel to keep us warm, the ice covering the planet would become our tombstone. During Snowball Earth, the only living things were single-cell bacteria. Even their survival seemed improbable. But here we are. Life clearly did survive. The question is, how? The quest to learn how ancient organisms kept evolution alive has brought this lone microbiologist to Whiteout Glacier in southern Alaska. Here, Hazel Barton studies how life could have survived a global deep freeze. Her mission is to find signs of life in some very dead-looking frozen caves.
People used to think that caves were devoid of life, that there was nothing in there. But it turns out they're actually teeming with microorganisms.
Barton's searching for modern-day microbes living in this ice cave to learn how their ancient ancestors endured the Ice Age 650 million years ago.
If you look on the edge of the cave, you can see all the particle dust that's got lodged in the ice. And it creates a surface that the microbes can actually live on.
The cave runs beneath the glacier. Inside, it's 4 degrees below zero. Creatures that live in such harsh conditions are known as extremophiles. Barton takes samples of the microbes buried in freezing rock sediments at the base of the glacier.
I'm looking for some sediments that might contain microbes that have never been exposed to the heat. So the thing we remember about these bugs is that they love the cold, and they've actually evolved to live in those cold conditions. And because of that, if I was to take them outside right now into the heat of the sunlight, they die. It would be like taking us into the middle of the desert and dropping us off there.
Barton believes this dark sub-zero cave can shed light on how microbes adapted to conditions during Snowball Earth.
The majority of surfaces exposed on Earth would probably have looked something like this. So we're looking at the kind of conditions that organisms that survived that period would have been living on.
They're not just living on the ice, they're living in it too. Sunlight penetrates a few meters into the ice wall, and that's enough for the microbes to flourish.
We're still pretty close to the entrance right here, so I think there's definitely a lot of sunlight energy and enough for cyanobacteria to grow on. And they're probably in the ice. They're living in the ice right now.
The deeper Barton goes into the cave, the darker and colder it gets. But even here, life hangs on.
This is a community that looks like cyanobacteria. They're incredibly resistant to all kinds of stress that you would put them under. They can survive it.
During Snowball Earth, the ice was thousands of meters thick, enough to block out nearly all the sunlight microbes needed to stay alive. Barton finds similar conditions even deeper into the cave. Here, there's hardly any light at all. But even in this dim, icy world, she finds microbes thriving.
So what we're looking at are microorganisms that have to adapt and generate energy when there is no sunlight. So what they do is they pull energy from the rock itself. They actually chew into the rock to get that energy.
Outside, Barton examines her samples on a field microscope. She believes these modern cyanobacteria have a similar structure to the ancient microbes that survived the Snowball Earth.
We're seeing cyanobacteria. There's a whole community living in that ice.
Cyanobacteria really are these amazing organisms. They're very, very adaptive. They're one of the most ancient forms of life on our planet. They can survive some really extreme conditions.
Cyanobacteria have evolved amazing survival mechanisms. If our cells freeze, they burst their walls. If they dry out, they die. But cyanobacteria have evolved a cell structure that prevents rupturing in some of the most extreme conditions on Earth.
They've changed the structure of their DNA so it doesn't get damaged. If you were to take us and dry us, then, our DNA would be irreparable. You do that to a cyanobacteria, and you just have to add water 100 years later, and within a few hours, it's starting to carry out photosynthesis again.
Just as some could cope with dry conditions, others could cope with ice. As the ice rolled over them, most microbes died, but the hardiest survived. Over time, strains evolved that thrived in the cold and dark, to become the ancestors of every living thing on Earth today.
Everybody thinks about these global catastrophes like it's going to wipe out all life. And it's like, no, these microorganisms have been going through similar things for billions of years. And they're adaptive and they change. And then they fill the niche that's left behind.
Barton's research proves that even in the most extreme conditions, in the ice, in the dark, life finds a way.
Short of an object the size of Mars hitting the planet, you know, life will go on Earth. And events that we may think are, you know, catastrophic just simply turn over a new leaf and we start seeing a different form of life on Earth.
The only reason we're here today is because life adapted and survived. But there's another puzzle. We're here, but the ice isn't. All that ice should have kept the planet so cool that it could never thaw again. And for 25 million years it did. Then something extraordinary happened. At 8:35 p.m. on our clock of Earth's history. The planet's surface had been locked in ice for almost 25 million years. But at 8:37, a remarkable thing happened. The ice sheets started to recede. Something was warming the Earth. But it wasn't the sun. Believe it or not, the thing that would save the planet was actually inside the Earth itself, buried deep below the ice. This is Mount Augustine in the Aleutian Islands, one of the most volcanic regions on the planet. Augustine has been active for over 40,000 years, and it's still erupting today. Volcanologist John Power is here to study what it tells us about the end of Snowball Earth. Because volcanoes are the only things on the planet hot enough and strong enough to thaw a frozen world.
We're on our way to Augustine Volcano. It's one of the most active volcanoes in the region. Last erupted in 2006. It all comes to play here at Augustine.
A fiery hell lies under Mount Augustine's frozen surface. During its last eruption, millions of tons of lava and ash exploded into the atmosphere. So much material spewed out, the volcano actually grew.
We're about 100 feet higher than the summit of the volcano was prior to the eruption. This is some of the newest land in North America.
Power uses a field thermometer to take a reading from just below the surface.
We've got a temperature of about 95, 96 degrees centigrade. So the summit of the volcano is still very hot. If you wanted to cook some potatoes, fry up some eggs, this would be exactly the spot to do it.
There's no doubt Mount Augustine is hot, but it's hard to believe a volcano, even one this powerful, could punch through an ice sheet several thousand meters thick.
Where we are now has been covered with glacial ice as recently probably as 10, 15, 20,000 years ago. This was all underneath a glacier at that point in time.
When Power examined volcanic rocks here, he found evidence that 24,000 years ago, an eruption smashed its way up through the ice.
There is absolutely no problem for a volcano like Augustine or its neighbors to erupt through an ice sheet that could be either several kilometers or several miles thick.
We know it's possible because we've seen it happen. In 1996, the Grímsvötn volcano in Iceland erupted right through a glacier. It punched its way up to the surface through a kilometre of ice. The torrents of hot gases and ash blew a giant hole in the glacier. it melted ice at a furious rate. Flash floods carrying 45,000 tons of water a second raged for hours. But on a global scale, that's nothing. When the whole world was frozen, a few little holes wouldn't have made much difference. Luckily, volcanoes have another formidable weapon in their arsenal. They spew out more than just lava and rocks. They also produce huge amounts of greenhouse gases.
Carbon dioxide is one of the very dominant species of gas that is coming out of volcanoes. There have been times when we've had certainly, thousands of tons per day coming out of this volcano.
Mount Augustine is dwarfed by the volcanoes that broke through the ice of Snowball Earth. Scientists believe that thousands of them ejected billions of tons of carbon dioxide into the atmosphere. Over a period of around 1 million years, this caused carbon dioxide levels to rise, reversing the depletion that created Snowball Earth and tipping the balance in the opposite direction.
Carbon dioxide rapidly built up in the atmosphere until it got to a critical point where we had a super meltdown of the ice, and that was the death knell of Snowball Earth.
The carbon dioxide-rich atmosphere trapped the sunlight, increased temperatures, and finally melted the ice. After a 25 million year freeze, Snowball Earth was over. As the ice sheets retreated, something remarkable happened. The greatest leap in the evolution of life the world has ever seen. A leap that would lead directly to us. In the oceans, a few single-celled organisms had survived. After the ice melted away, they began to change dramatically. Roughly 3 million years after Snowball Earth ended, the new, warm climate triggered an evolutionary explosion unlike any other. Single-celled bacteria evolved into multi-celled creatures. The first ever complex organisms and the ancestors of all animals, including us. It was the dawn of a new era for life on Earth.
Snowball Earth must have been the closest thing to extinction of early life on Earth that we had. And yet we know creatures survived. And it can't be a coincidence that very soon after the waning stages of this Earth-wide ice age, we get the first large creatures. It really seems as though that series of environmental catastrophes spawned the kind of biology that could give rise to multicellularity.
The key to this evolutionary revolution was oxygen. Before the deep freeze, oxygen levels were only 1%, too low to support more complex organisms. After the freeze, levels rocketed to 21%. Scientists suggest the boost in oxygen levels was the result of Ice Age chemistry. During Snowball Earth, the sun's ultraviolet rays reacted with water molecules in the ice to produce a chemical called hydrogen peroxide. When the ice eventually melted, the hydrogen peroxide broke down again, releasing huge quantities of oxygen into the air and oceans. The surge in oxygen levels provided the fuel for life to evolve from single to multi-celled organisms. They don't look like much. They're only the size of pinheads. But these tiny creatures are the oldest multicellular fossils on the planet. The first links in the evolutionary chain that eventually led to advanced animals and humans. In the new oxygen-rich atmosphere, these creatures became more and more complex, from just a few cells bound together to creatures large enough for separate groups of cells to assume different body functions. Over millions of years, these specialized groups of cells evolved into the first organs, and that paved the way for ever larger and more complex anatomies. In Australia, Jim Gayling studies the fossil remains of the creatures that inherited the planet after Snowball Earth.
After Snowball Earth, we see a revolution in the history of life from the fossil record, because for the first time, we see large creatures, creatures that anyone can see with the naked eye. They are the first animals on Earth.
This primitive sea creature is one of the first complex multicellular organisms. It lived and died around 50 million years after the end of Snowball Earth.
It's absolutely complete. You can see the gut, you can see the head end where the segments wrapped around it, and these incredibly fine segments just wrapped over the sea floor.
All the animals on the planet, including us, are descended from creatures like this.
You're looking at the first life forms which had patterns of cells and body plans that were the same as ours. Head, a tail, a belly, a back. Even though they're not necessarily our direct ancestors, these are the first creatures that represent the line of biology that gave rise to us.
All over the planet, similar organisms were evolving, making the leap from primitive to complex life.
There'd been life on this planet for more than 3 billion years. And it was really only the Snowball event that kick-started complex life. If it hadn't been for this ice age, this would have been slime world forever, and we wouldn't be sitting here talking about it. So, if you want to put your finger on one point in the history of life that made a big difference, that was Snowball Earth.
From slime to this, complex life in all its vivid, colourful, infinite glory. All of this, you, me, every living thing on the planet, is here because of an evolutionary explosion 650 million years ago, of a catastrophic deep freeze that threatened to wipe all life off the Earth, but ended up creating life as we know it. If it wasn't for Snowball Earth, we probably wouldn't be here. In the next episode of Catastrophe, massive volcanic eruptions kill off 95% of all life on Earth in the biggest wipeout of all time. But remarkably, this new catastrophe triggers the evolution of the most successful creatures ever to walk the planet, the dinosaurs. When I look around at all these people, it's hard to believe quite how lucky we are, because we're only all here by chance. Evolution wasn't an orderly progression from single cells to us. It was an imperfect, often violent process, and it's a miracle that we're here at all. In this series, we'll look at the theories about catastrophes that shaped our world and very nearly stopped evolution in its tracks. Like the time the planet was encased in ice for 25 million years, freezing the land and the oceans. Life survived, but only just. When huge volcanic eruptions poisoned the planet's atmosphere and pushed all life to the edge of extinction. Or the moment a 6-mile-wide asteroid smashed into the planet, killing 70% of life on Earth including the dinosaurs. Even humans didn't escape unscathed. We might only have been around for a short while, but we've faced and survived supervolcanoes, ice ages, and even cosmic impacts. These catastrophes nearly wiped out life, but from their ashes, new species evolved. Without them, we might not be here at all. Tonight, we examine the first great catastrophe, the day our planet collided with another. The Earth's around 4.5 billion years old, so it's tough getting a handle on such an enormous amount of time. To put it in perspective, imagine the whole of Earth's history compressed into the 24 hours of a single day. Each minute on our clock represents around 3 million years. It starts ticking at midnight, and the first catastrophe was just minutes away. Our solar system hadn't even finished forming. 20 infant planets circled a new star, our sun. One of them was Earth. Its surface was a vision of hell, a barren, lifeless place shrouded in toxic volcanic gases. There was no water, no oxygen, and no moon. But this is all about to change. As our clock reaches 9 minutes past 12, that's 4.5 billion years ago, the Earth faces its first and greatest disaster, an impact of biblical proportions. Reconstructing Earth's early history is a major challenge. It's been obliterated and obscured by billions of years of erosion and volcanic activity. Astronomer Bill Hartmann has spent his life studying the events of the early solar system.
The record of the very first part of the Earth's history, all of that is wiped away on the Earth itself because we have erosion and rain and continental drift and continents colliding and mountains coming up and so on.
But all is not lost. There is a record of Earth's earliest days, just not on Earth. It turns out the best place to look is on nearby Mercury and Mars. Their surfaces have barely changed in over 4 billion years, providing us with a unique record of events in the very earliest days of our solar system. They're dotted with ancient impact craters.
You start looking at those craters and you discover that there are not only 100-mile craters and 200-mile craters, there's 600-mile features. I mean, some very large objects.
These craters paint a picture of an intensely violent period, of a solar system littered with cosmic debris, where millions of asteroids and comets smashed into the young planets. In the thick of this all-out assault, the Earth too must have been struck.
It was a window into the early history of the Earth, and it made us realize that the Earth itself has had this tremendous history of impacts, enormous impacts that could have really damaged the whole planet. It got people thinking about what would be the effects of giant impacts on the Earth.
Hartmann realized that it wasn't just small asteroids hitting the planets. There were much larger objects too. And the larger the object, the more dramatic the consequences.
So the impact process, it's a wonderful kind of paradox. On the one hand, the small impacts tend to make everything the same, millions and millions of impacts averaged out, but the big impacts give individual personalities to the planets.
Take our planet, tilted on its axis at 23 degrees, with a nearby orbiting satellite, the Moon. We used to think that they'd been born together, until Hartmann proposed a radical theory. The Earth had been hit by something the size of another planet, creating that tilt and the Moon.
The key to our idea was that as the planets grew, you had the finished planets, but you still had leftover bodies. If one of those crashes into the Earth, just as the Earth has finished forming, that can blow out material from which the Moon could form in orbit around the Earth.
Picture the scene. The newly formed Earth hurtling round the Sun, and loads of other planets doing exactly the same thing. Including this one, Theia, about the size of Mars. It was orbiting the Sun at exactly the same distance as the Earth. The two planets were on a collision course. Theia hit the Earth at 25,000 miles per hour, with the force of billions of megaton bombs. The impact ripped off huge sections of the Earth's crust. Billions of tons of debris blasted into space. A ring of red-hot dust and rock formed around the Earth. Over the next 100 years, the rocks and dust slowly clumped together into a ball 1/50th the size of Earth. We call it the Moon. When Hartmann suggested the idea in the 1960s, people found it hard to accept.
Scientists were thinking of everything in terms of slow geologic processes, one grain of sand at a time, you know, wearing down mountains. To think of something as colossal as the Moon forming as a result of a single event was hard for people to swallow.
But then Hartmann got the first real clue that his theory might be true. The Apollo project.
That's one small step for man, one giant leap for mankind.
American astronauts made 6 visits to the Moon. They explored its surface, drove around its craters, and brought back 840 pounds of Moon rock. For the first time, scientists could find out what the Moon was actually made of. The lunar samples had a remarkably similar chemistry to the outermost layer of the Earth's crust. To most researchers, it was an interesting discovery. But to Hartmann, it was vital new evidence.
So you have crustal rocks, you have rocks on the surface, and a big impact comes in and blows all those crustal rocks away. And that material goes into space and forms the Moon.
But many scientists were still skeptical. They just couldn't see how a massive impact could create the Moon and the Earth as they are today.
I actually had people telling me we should exhaust every other theory first because this was such an outlandish idea.
It was a chance meeting at a conference with astrophysicist Robin Canup that gave Hartmann the breakthrough he was looking for. She was using computer models to study Saturn's moons.
Bill Hartmann came up to me after my talk and asked me, have you ever thought about applying your models about how moons form within and near Saturn's rings to the origin of the Moon? And I said no.
So she tried it. Canup used modeling software to recreate the early solar system. Then she plotted a planetary collision of the kind Hartmann was suggesting.
So we're 4.5 billion years ago, at the end of the Earth's formation, and we're in space, And we're watching as a small planet, the planet on the right, is about to hit the young Earth, represented by the larger planet on the left. The collision takes place, and as we see it hits in a glancing blow. And you can see the impactor is completely destroyed by the collision.
Theia, the impactor, is annihilated. Earth survives, but only just.
Now, this collision is incredibly violent, so violent that there's enough energy to completely melt the Earth. And in fact, at the end of this impact, the Earth is surrounded by an atmosphere of vaporized rock.
Trillions of tons of debris blast out into space.
Here we see part of the impacting planet sheared out into this long arm of material that produces a disk that we're seeing almost edge on in this view. And it's from that disk that the moon later coalesces.
Canop's model demonstrates that the moon was probably made of debris from both Theia and Earth. It explains why those moon rocks were so similar to rocks from the Earth's crust.
So I actually called my colleague and said, "You're not going to believe this, but I tried this Mars-sized impactor case with about a 45-degree impact angle, and everything worked." And he said, "You better check it again." And so I did check it again and did many more of these simulations, and sure enough, that type of impact is the one that gives us the Earth-Moon system today.
Canop's work was further evidence that Hartmann's radical theory might just be right.
So it was very exciting as Robin did her models and they started to say, yes, there can be moon-forming debris left in orbit around the Earth, and the moon would form from that debris.
Hartmann and Canop's work showed that our moon was created by a violent cataclysmic collision between Earth and its twin Theia. The Earth narrowly survived complete destruction, but the collision triggered a series of events that transformed our planet. It became a climate hellhole with extreme weather conditions and giant tides. But bizarrely, those deadly conditions created the building blocks for life itself to evolve. On our clock, only 10 minutes have passed. That's 30 million years in real time. It was the single most important period in the Earth's history, a time of incredible violence that saw the creation of a new Earth and our moon. The massive impact which created the moon very nearly destroyed our planet. But out of this catastrophe came a new beginning, because the impact set in motion a chain of events that transformed the Earth from a vision of hell to the blue-green oasis we call home. Scientists set out to reconstruct those events, starting with the moments immediately after the impact. Ithaca, upstate New York. Paleontologist Judith Nagle-Myers hunts for clues that might reveal what happened to Earth just after it was struck. No evidence remains on Earth from the time of the collision, so scientists are constantly searching for ingenious ways to look back in time. Nagle-Myers uses fossilized corals. These ones are just 400 million years old. But they hold a vital clue to what conditions were like on Earth 4.5 billion years ago.
Personally love about fossils that you find them and they open up a window in time. Just by looking at their remains and their skeletons, you can reconstruct the environment that was here long before humans are even on the Earth.
The coral fossils have an unusual property that allows them to capture a day-by-day snapshot of conditions on early Earth. They lay down layers of limestone, a new layer for every day of the year. You can see the same process in every reef, including today's coral.
If you actually look closely at these modern corals, you can see tiny lines that they built while they're growing. They're kind of similar like growth rings on trees. We know nowadays that one of these lines represents a day.
The daily growth layers build up to create a larger annual ring.
If you count these daily growth rings, you can actually, in modern corals, count 365 growth lines per year.
But the 400-million-year-old fossilized corals don't have 365 growth lines per year. They have 410. When these corals were alive in the ancient oceans 400 million years ago, the world was very different. A year didn't last 365 days, it lasted 410. But whether you measure it in days or hours, the Earth's orbit around the Sun always takes the same amount of time. A year is always constant. The only explanation for more days in a year has to be that millions of years ago, each day was shorter.
That means that back in the day when this animal was actually living in the ocean, that the days had less hours than they have today.
400 million years ago, a day lasted just 21 hours. And if days were shorter, then the Earth must have been spinning faster. Calculate back from 400 million years ago to 4.5 billion years ago, just after the huge collision, and each day would have lasted just 6 hours. And that means the Earth must have been spinning much faster than it does today. It seems the massive impact that created our moon also set the Earth spinning like a top. It was the first step towards the habitable Earth we live on today. But you'd never know it. The rapid rotation unleashed the worst weather the planet has ever seen. It looked as though the collision with Theia had left the Earth an uninhabitable world. At 12 minutes past midnight on our clock, 40 million years after the Earth first formed, frozen comets started smashing in from space. It was a savage bombardment, but it wasn't a disaster. In fact, it was a blessing. The icy comets melted, helping to create the first oceans. But the young Earth was still a violent, hostile place. Its rapid rotation whipped up 500-mile-an-hour hurricanes. Rain and storm-force winds scoured the planet's surface. And the atmosphere was a lethal cocktail of carbon dioxide and acid rain. It seemed that there was no way life could ever have got started. Were it not for one thing. When the moon rose 4 billion years ago, it wasn't the familiar moon we see today. It was 10 times closer to the Earth and dominated the horizon. Its proximity was another consequence of that huge collision. One that led directly to the emergence of life on Earth. Because the moon was so much closer than today, its gravitational pull on the Earth was much stronger. It pulled hard on the Earth's newly formed oceans. The result, huge tides that ripped across the planet at hundreds of miles an hour. You might think these made it tough for life to get going, but you'd be wrong. This is the Bay of Fundy, Canada. It has the highest tidal range on the planet. And that makes it the closest we can get today to the colossal tides of early Earth. Physicist Neil Cummins is here to study what happens when the tide comes in today, and what that can tell us about tides in our planet's distant past.
What I would expect to see here is a huge wave, maybe 5-6 feet high, called a tidal bore.
He's waiting for the tidal bore to surge in at high tide so he can see at first hand the kind of forces that shaped the ancient landscape and created the conditions for life to begin.
Right up here, actually, in the middle of the channel, you can start to see the tidal bore. You can see the wave curling over.
Yep.
See the white water.
It's absolutely fascinating. Sounds like
you can actually start to hear it a little bit.
You have a feeling that there's an action here that you don't see anywhere else.
Should we go and meet it?
As the incoming tide surges upriver, it meets the outgoing tide, creating one of the world's largest tidal bores. The rushing waters smash into the edge of the bay. They rip sand, minerals and other material away from the shore and carry them out to sea. Fundy's tidal bore replicates in miniature the tides on the early Earth.
The ancient tides would have been at least 1,000 times higher. There's a tremendous amount of power in these tides, but nothing compared to what it was. This bore is traveling about 12 kilometers an hour. The ancient tides would have been traveling on the order of 100 to 300 miles an hour. And they would have gone much farther inland, much faster, and would have done much more damage.
"4 billion years ago, when the moon was much closer, the tides would have smashed inland at hundreds of miles an hour. Each tide churned up millions of tons of debris. When it retreated, it left a devastated coastline. The young planet Earth was being devoured by its oceans. And for us, that was good news. Because what the tides stripped from the land, they gave to the ocean, creating the perfect environment for life to emerge.
To get life started, you need a huge amount of minerals in the oceans that are free to mix and interact. The only way that the Earth could have gotten that was from the huge tides that the moon gave when it was much, much closer.
The tides ripped minerals and nutrients from the land and mixed them into the oceans, creating a primordial soup. Scientists think that chemical interactions in that soup created the very first amino acids and basic proteins, the building blocks of life. From these ingredients, the first primitive cells would eventually emerge. Life that might never have developed were it not for the tides. Tides created by the moon, a moon born out of catastrophe. A disaster that nearly destroyed the Earth, but without which life might never have evolved. But the Earth was still a brutal place. The planet was spinning wildly. The climate was too chaotic and the seas too brutal for single-celled organisms to evolve. But beneath those churning seas, a vital concoction was brewing. A few simple strings of molecules were assembling, and those molecules would be the precursors of life. It's 3:20 on our clock of the Earth's history. It's 500 million years since the impact that created the planet and its moon. Thanks to the moon's violent tides, the first building blocks of life have been created deep in the ocean. But the tides are too violent to allow the organisms to evolve. Something must have happened to calm the planet and allow life to take the next step. Otherwise, we simply wouldn't be here. This is KwaZulu-Natal in South Africa. For paleontologist Nora Nofka, this ancient gorge is a truly remarkable place. Here, she discovered fossils of some of the earliest forms of life on the planet. 3 billion years ago, this landscape was an ancient sea teeming with single-celled bacteria. A billion years after the catastrophe that nearly destroyed our planet, life on Earth was in full bloom.
It was really one of the great moments in my career. We were searching for fossils the whole day long, and then in the late afternoon, when the sun was shining in the right angle, suddenly we saw the fossils popping out everywhere. It was just unbelievable.
The fossils were the remains of vast colonies of bacteria that grew as mats in shallow oceans. And they were some of the earliest living cells to inhabit the planet. There are bacteria very similar to these still alive today.
Those are living bacterial colonies. We term them microbial mats, and you can easily see why. Those mats look like little greenish carpets. They occur today everywhere, the sandy beaches.
The similarities between ancient and modern are striking.
You can see the rock surface is greenish colored, just as the living microbial mat as well. You follow my finger now, I show you the edge of the fossil microbial mat here. And here you see the sand underneath is such a microbial mat like this piece here, but it's fossilized and it's 3 billion years old.
The rocks all over the gorge reveal an astonishing diversity of ancient microbial communities. Ecosystems of bacteria as complex then as they are today. But the rocks reveal something else. They show not only when cellular life took hold, but how it was able to do so. Because when life emerged, it wasn't in the violent oceans left behind by the collision with Theia. It was in calm, shallow water.
Came first here into this outcrop, into the side. I saw all those different ripple marks, and they look just as they do nowadays. If you walk along a beach, you can see the same structures in the sand. So the preservation of those structures is just outstanding here.
It looks as though the tide has just gone out. Except these ripples are 3 billion years old, the fossilized record of an ancient ocean gently lapping the shore. With no sign of giant tides or hurricane winds.
The site shows that at least 3 billion years ago, the living conditions were normal. This is a peaceful environment here, so life could evolve.
Something had changed the planet's climate, making it hospitable for life. And once again, that something was the moon and its effect on the oceans.
The tides, since they've started forming, have acted as a brake to slow the Earth's spin. You can almost think of it as the brakes on a car, pressing on the tire and causing the two to slow down together. That's what's happening and has happened from the tides.
It's a process called tidal friction.
When the tides and the continents meet, the water pushing against the land creates friction. And that friction is literally slowing the Earth down.
Gradually, over millions of years, the Earth began to spin more slowly. As a result, the days became longer and the hurricane winds subsided. It was a step in the right direction, but on its own, it wasn't enough to create the calm seas we saw fossilized in KwaZulu-Natal. The moon was still close to the Earth, its gravitational pull on the oceans still strong. For the oceans to have calmed to a gentle ripple, something major must have happened. And the answer to what did was discovered in NASA's Apollo program, the final leg of man's mission to the moon. The McDonald Observatory, USA. Here, 40 years after man first landed on the moon, the Apollo mission is still going strong. Every day, NASA engineer Jerry Wyant rides up to his laser telescope in this remote part of Texas. His mission: to measure the moon's distance from Earth.
We're the last living piece of the Apollo project. And most of the public thinks that, oh, the Apollo project's they're dead and gone. And so they're surprised when I tell them what I do, I send a laser to the moon.
When astronauts landed on the moon, they left behind the American flag and something else: reflectors. Almost daily, Jerry Wyant and his colleague aim their laser at one of the lunar reflectors. They're measuring the precise distance between the moon and the Earth.
This is a 1 billion watt laser. We direct it at the reflector on the moon, and we measure how long it takes for this light to go from here to the moon and back, and that's our data.
The laser measures the time it takes light to bounce back from the moon to a trillionth of a second. But first, they've got to find the reflector.
Each panel is about the size of this map right here. So if you think about it, we're trying to hit something this size about 240,000 miles away. It's not easy.
They need a clear night, then they need to locate the target.
Yeah, they all look alike, don't they?
Yeah, so it's easy to get lost.
It can take up to 4 hours just to find the reflector.
Well, that right there, that would be the reflector on the moon, right there.
Tonight, the laser beam takes 2.3967 seconds to travel to the moon and back.
When I see the moon in the sky, instead of thinking romantic thoughts, I think, gee, I hope the laser's working okay.
It may not be romantic, but it is amazing, because each year, Wyant's laser beam takes a little longer to bounce back. That means each year the moon's a little further away.
One of the reasons that scientists want our data is to confirm their suspicion that the moon really is moving away from the Earth. And they've used our data to report back to us the value of that. In fact, is yes, it really is.
The moon is spinning away from us at 3.4 centimeters per year. And it's this that holds the key to understanding why the oceans calmed and life emerged. 3.5 billion years ago, the moon was only 15,000 miles from Earth, resulting in mountainous tides. But bizarrely, these tides were pushing the moon away. They were so huge, they had a gravitational pull of their own, and that began to affect the moon that had created them.
The gravity from the water is acting back on the moon, which raised the water up in the first place. And this water is pulling the moon forward, giving the moon energy.
As the Earth span, it slung the moon further away, like an athlete throwing the hammer.
You can think of the Earth-Moon system as waltzing together. As the moon creates the tides on Earth, the Earth is slowing down, and the tides are causing the moon to gain energy and spiral away. The two have been doing this dance for 4.5 billion years.
So the catastrophe that nearly ripped our planet apart before life even started actually ended up making life possible. Violent tides filled the sea with vital chemicals. Then the Earth's spin slowed and the moon drifted away. The nutrient-rich seas calmed and life got started. But this new flourishing life was about to face another catastrophe, a disaster that would wipe out much of life on the planet, but without which we probably wouldn't be here. Some bacteria began to release a deadly poisonous gas called oxygen. It's 8:10 a.m. on our planetary clock, just over 1.5 billion years since the Earth was born. The first third of the Earth's life was violent, chaotic, and lifeless. Then the climate stabilized and life began to take hold under the seas. But suddenly, some bacteria underwent a change that would affect all life on Earth. It wiped out many species, but without it, no complex life, none of this, would be here at all. This barren landscape is the high desert in northern Mexico. It's one of the only places in the world where we can get a glimpse of what the Earth might have been like 3 billion years ago. Biologist Janet Seifert studies the bacteria that live in these pools. They give her a unique insight into how ancient bacteria changed the Earth forever.
You can walk out to the pools and you can see evidence of microbial communities with the naked eye. Now that's very similar to what early Earth was like. Early Earth was certainly dominated by bacteria. There were no large animals or plants. So we can use this as a proxy for early Earth.
These odd-looking lumps are particularly interesting.
So this is actually quite remarkable. I know it doesn't look remarkable. This looks like just a rock found in the bottom of this little river here, but this is actually a complex community of microbial life.
These lumps are called stromatolites. They're made of bacteria that deposit limestone, building up to form these mini reefs. It was organisms almost identical to these that populated the early Earth. These fossilized stromatolites in the Flinders Ranges in southern Australia are 3 billion years old. There's virtually no difference between these and the living structures Seifert's studying in Mexico today. Each stromatolite contains millions of blue-green organisms called cyanobacteria. And 3 billion years ago, their ancestors evolved an ingenious means of obtaining energy.
One branch of bacteria actually learned how to do one thing. They just used the sunlight for energy, but as it turned out, when they did that, they did it in such a way that they could split water and create and give off as a byproduct something they didn't want, oxygen.
These ancient microscopic cyanobacteria evolved a chemical process called photosynthesis. It converts light into chemical energy, with oxygen as a byproduct. It was a biological revolution, and it changed the planet forever. Cyanobacteria pumped oxygen into the oceans, then the atmosphere. Without cyanobacteria, we could never have evolved. It's thanks to them that we breathe oxygen today. If they hadn't invented photosynthesis around 3 billion years ago, there'd be almost no oxygen in today's atmosphere.
Once the cyanobacteria figured out how to produce oxygen as a byproduct, it changed our planet forever. It changed the way biology was going to evolve, and it changed the atmosphere completely.
It's a process that continues today.
I remember the first time I was swimming around down here, and you could see the small little bubbles accumulating underneath the ledge of the stromatolite. It was quite amazing to think that that process that we were actually visualizing in that way is what's creating the atmosphere today.
And those ancient cyanobacteria are the ancestors of every plant in the world today. Photosynthesis was incredibly successful. The bacteria flourished and evolved.
We always think about microbes being something bad and giving you strep throat. But if bacteria hadn't been able to harness the sun and then as a byproduct produce oxygen, you and I probably wouldn't be here now, because it's what allowed complex animal evolution to occur.
There was just one problem. 3 billion years ago, oxygen was bad news.
When it first happened, that byproduct oxygen was poison to most of the life on the planet. So it was a devastating thing that happened. All of life had to actually acclimate to the fact that there was oxygen in the atmosphere.
But a few bacteria did learn how to handle it, and it's those ones that led to things like us.
Actually, I feel pretty lucky, because that bad poisonous gas that cyanobacteria had as a byproduct, if it hadn't accumulated in the atmosphere, then I wouldn't be here. So as far as one of the major biological innovations that happened in 3.8 billion years, it has to be up at the top of the list of one of the best ones for us as humans.
By 8:12 in the morning on our clock, the atmosphere had oxygen and the oceans were teeming with bacteria. Evolution, life, had begun, and it all started with a catastrophe. That impact is the only reason life ever evolved. But if it had been even slightly different, there might be no one here at all.
If you consider all the different types of impacts that could have happened and have left Earth-Moon systems that weren't nearly as habitable as our own, it's really quite something to think that we got lucky in a sense.
And that's the point. We did get lucky, not just with that first impact, but in countless ways over billions of years.
What we're realizing now is that catastrophes have played a much larger role in the evolution of life on Earth than anybody believed earlier. You have to realize that we are at the end of this long chain of unique events. Had they played out differently, this guy wouldn't be sitting on this rock here.
There's only one conclusion. We're not here because we did something right. We're here because we're lucky. The collision with Theia was just the first of many random rolls of the dice.
It really makes you think about this completely unique sequence of random events that were all necessary to give us the Earth we know today. And if any one had just been a little different, the whole world around us would be different. We wouldn't even be here. It gives you an appreciation that a catastrophe is always, in some respects, a beginning.
The collision was the beginning of a new Earth. It set Earth apart from all the other planets in the known universe and started us off on the long and difficult journey to life as we know it. And without it, this city, the people in it, you, me, we probably wouldn't be here at all.